Okay, next and the last presentation will be given by Naeem and Naguib, Team 1. They will talk about the restricted Boltzmann machine training of perceptron for clustering. They will use about 40 minutes, and we will have about 10 minutes for discussions. Okay, start.
Thank you, and hello everyone. I will try to explain what we are trying to do in the final project. So first I will explain the abstract. Although there are traditional classifiers that are well developed and so many people are using them in the 90s, they have some limitation in the sense that when we use a classifier like a support vector machine or a naive Bayesian classifier, we have to set the features. We have to design the features and engineer these features and maybe handcraft them based on the objects and the target objects we are looking for. This is a limitation because this means that whoever designed this system must be an expert. Otherwise, it will not work. And the other problem is after we finish training, if there is a new object coming in, we cannot retrain the network, the system. We have to rebuild the whole system from start. So these are the limitations of traditional classification techniques, and many people are interested in neural network because neural network have the promise of removing this limitation. But neural network had so many trouble in the past because the computational power available for the people at that time was not very much, so they could not go very deep. And shallow network, as we will see in here, are not really good. So they were not able to overcome the traditional classifier. However, in 2012, two main factors allowed this neural network to go viral, and everyone nowadays are really interested in them. One is within these 10 years, we have so many order of magnitude better computers and better performance we can get, especially for GPUs, that allowed this computation to be much faster. So instead of training a network on a CPU in 1 month or 2 months, you can train it in literally like few hours on a multi-core GPU. The second factor is especially the work in Hinton and in Toronto University that allows neural network to be trained unsupervisedly. So we don't have to have a massive number of labeled data, which is very costly and most likely is not available. We can actually give it raw data, like pictures taken by random people in the street. We don't need labels. We just give this picture as it is to the network, and it will be able to train unsupervisedly. So this enabled the network to access massive amount of data because they don't have to be labeled. So based on these two factors, the success of, in particular, AlexNet in 2012 was really remarkable, and everyone started to pay attention to these topics, and we are also interested in studying it. In our project, this is actually very complementary to the work done by Team 2, by Pio, and we are very thankful for his presentation. It is really insightful. So I will not go in much details in parts that he already covered. I will try to complement his presentation as well. In our work, we are interested in particularly in this unsupervised pre-training. One of these techniques is called restricted Boltzmann machine. So we want to understand how this training is useful. And also, in particular, we want to understand the neural network in a very fundamental level. So we want to understand the perceptron and how a perceptron behave. Professor also asked us to do some original idea. So one thing we try to do in order to understand how perceptron work is to apply it in a new field. Usually neural network and multi-layer perceptrons are used for classification purposes. Here we try to think, since it is unsupervisedly trained nowadays by RBM, how about we try to use it for clustering? And that is the main purpose for our project. So in this project, we will introduce an approach using RBM perceptron layers and try to train it on a data set and see if it can produce a good clustering behavior or not. And we will compare this clustering behavior with respect to state-of-the-art clustering techniques as well as classification techniques. The evaluation methods in clustering techniques is going to be self-validation, and in classification techniques it will be cross-validation. And we will use the evaluation criteria as the success rate. And we will show the result in this paper, in this project. So the goals of what we are trying to do right now is first and foremost understanding what the perceptron behave and how it behave. This is the very fundamental unit of a neural network. Understand the training techniques and in particular RBM and how can we use RBM to perform clustering. Compare this approach with other clustering techniques and other state-of-the-art classification techniques. These are the goals of our project. The new ideas in this project is to use this multi-layer perceptron. In our case, we will use a single-layer perceptron and train it by RBM and see if, explore if this can be used as a clustering technique or not. So the first step of our paper is going to introduce the clustering techniques that we will use for comparison. I think most of us already know them, so I will skip most of them. K-mean clustering, it's very well known and we studied a lot, and I think team 3 perhaps made a very good presentation in which they improved this by using spectral analysis. Density-based clustering, I think also team 3 briefly mentioned it in their presentation. Basically, we look at the points and the neighboring points, and based on their density, we allow them to grow. So the clustering behavior become based on the density, not based on the partitioning of the space. Partitioning around medioids. This is one approach introduced by these people, in which they define something called dissimilarity matrix, and based on this dissimilarity matrix, they can partition space, and they have the advantage that they can actually estimate the number of clusters. They're just like the idea, similar to the idea introduced by team 3. So these are the clustering techniques. In terms of classification, we will use support vector machine with 4 different kernels: linear, polynomial, sigmoid, and radial. And we will also use naive Bayesian classifier. So these are the techniques we will compare our approach with. So what is our approach? First, let's understand how perceptron work. I think just now team 2 introduced how perceptron works, so I will also repeat some part of it and explain it in a little bit deeper level. So basically, let's say that we have some set of input. So this input are number of points. We want to make a linear combination of them. So we need to multiply each of this input by a particular fixed weight, and then add all of them together. So this will be a linear combination of them, and then do some kind of a nonlinear activation function and get an output. So in order to understand it, I will quickly give a very simple example, maybe at here. So let's say that I have a simple network of 2 input, x1 and x2. So this one will be multiplied by w1, this one multiplied by w2, and then summation. So the output at here is basically w1 x1 plus w2 x2, and we also allow bias to come here. So this means we have a bias. So this is the function that we have at here, right? We go through an activation function. So I'm going to use a very simple activation function, which is unit activation. So this means that if this value is above a particular threshold, in this case 0, then this would be either 1 or 0 based on this condition. So this function is equal to 1 or equal to 0 if this value is greater than a particular threshold, right? So if I put it in this formula, if w1 x1 plus w2 x2 is greater than or less than minus b, or b, we can define b as minus, this will tell us this is class 1 or class 0, right? If I draw this in 2D space, so this is x1 and this is x2, this relationship is a linear relationship, which means that this classification is actually aligned, right? So one area of this line will be classified as 1, the other side of this will be classified as 0, right? So what this perceptron is doing is actually using a linear classification of this space, doing a linear classification. In high dimension, this is called hyperplane. So this is dividing the space into 2. Usually we don't use this unit activation, we use something like a sigmoid. So what sigmoid will do is it will make this boundary a little bit fuzzy. So it will not be just boundary, it will be a little bit fuzzy. So if we go from here to here, we will not just sharply switch between 0 and 1. We'll slowly switch between 0 and 1 based on this sigmoid. And sigmoid is very well used because we can control this temperature, so we can smoothly control it in well way. So One single perceptron can perform, we can think about it, is it can perform like a linear classification. Activation function is also one important factor. There are many approaches of using different activation functions. In particular, most of the people use either a step function, just like the one I just showed you. Sigmoid is the most commonly used right now. They also call it logistic regression, and we can control the temperature of this sigmoid. So we can actually convert it into a step, or we can make it mild. Softmax, which is some kind of a normalization of exponential, and hyperbolic, and which is the hypertangent. So these are the distribution of them. Most of them are bounded from 0 to 1, except for the hyperbolic. It can go from -1 to 1, which can generate a good or bad behavior based on the application, because it can give a penalty. -1 is thought of like a penalty. So these are the activation functions. As I explained, one perceptron can generate this hyperplane. But if our classification requires not the hyperplane, but we need somehow a convex area, like the XOR problem. I think you know the problem of XOR, right? If we need to classify this. So we cannot use one line to classify it, right? But we have to classify it by a convex space. So we can say this space belongs to O, which means this is a convex space. So we need a convex space, and the convex space can be done by 2 layers. 2 layers is very simple. We can just use maybe, for example, one layer like here, and maybe one layer like here, and then make another system that will tell us if this side or this side, they are combined. So this is the meaning of 2 layers. When we apply 2 layers, the upper layer will take the output of the first layer, and then we can apply this boundary. If our classification space is not even convex, it's concave or even arbitrary, we need more than 2 layers. So that is the reason for people going to like a high level of large number of layers and going deeper in the network because of this classification approach. So this is for the network. Then how we train them? There are approaches that use supervision and unsupervised data. Mainly people use here the backpropagation and RBM. I'm not going to go in detail of the backpropagation net here, but I will briefly explain the RBM. RBM assumes that we don't know the label. So we need to train the network without even knowing if the label is right or left. In order to do that, the main concept is it's very similar to what we do in human brain. When you look at the like young born child, when he learns around in the world around him, he doesn't get the label every time. When he look at the chair, he doesn't know this is a chair. He just think about this as a new concept and then associate this with some help and then try to mimic it several times. Basically, when he go to sleep, his brain will go into some sleep stage in which he will reconstruct in his dreams what he saw in the morning, and this is exactly what RBM is trying to do. We have an input. Based on this input, we go through the network and generate the output. Based on the output, we will expect what input can generate this output based on our weight. So this is called reconstruction, and this is the kind of a sleeping stage. We will reconstruct what we get as an input, and then compare the actual input with what we reconstruct. And if we have an error at here, we can start to do gradient descent to improve this error. So that is the very basic logic. In mathematical formula, it is here, but I will not bore you with this mathematical formula. But the main concept is, since we don't have label, we can assume the input itself to be the label. And when we go up in the network, we go back to the input by reconstruction, and then compare what we reconstructed with the actual input.
Let's pause.
So as Pio said, in terms of backpropagation, the derivative of the activation function is almost everything. So when we selected the activation function, we select activation functions that are very easy for derivation. That is why most of the time it consists of exponential family. That is the main reason for this.
Much better.
Thank you. Okay, so now let's go back. I will not go in detail of backpropagation. I will focus more on the RBM. So RBM, as I said, doesn't assume that I have a label, so I cannot construct an error weight, and I cannot backpropagate it through the derivatives. So instead, based on the input, we can generate the output based on the current weight of the system, and then from this output, we can regenerate the expectation of the input based on the weights we have. Based on this expectation, we can look at the actual input and use it as a labeled data and find the error between what we expect the input to be and what the input is right now. And based on that, we can correct our weights. We can update our weights. This is the very fundamental logic about it. Mathematically, it is here, but as I said, I will try to avoid the mathematics here. So now let's go to the evaluation. I will try to explain what we are trying to do in the evaluation in more detail. We need a data set to experiment on. Usually people use MNIST, which is a handwritten data set, and they use it to evaluate a classification problem. And here we are interested in clustering problem, but we still use this data set. But we introduced a second data set that is well suited for clustering. We found on a website of a company that is called MaxMind. They provided an exhaustive map of the cities, almost 3 million cities. Each city include the name of the city, the country name, the region, and almost every other detail. For instance, we can get like all the names of the cities and the country name for it, and what is the city accent in the local, how people locally can call it, what is the region of this city, and what is the latitude and longitude. We use this data set for testing. In particular, we use the latitude and longitude as a random variable and the region as the label. And we hide the region first. So we assume we don't know the region. And we start with only latitude and longitude and try to do clustering only based on these two. Second is, we didn't deal with the 3 million cities. We constructed a subset of them. So we only selected the cities that belongs to Korea, and they are 44,000 cities. So this is the original data. If I cluster them based on their region given by the report, they will... I have all the list here, but I don't know Korea that much, so I cannot tell.
In Korea,
I found
we have, I think we have about 100 cities, and Myeon, Dong. I think you count as Dong. Dong, yeah.
I think
It's a village, actually.
yeah.
So it's a
I was curious, and I checked Egypt, and I found so many cities that I didn't even know about. I think they are very thorough in their report.
Yeah. When we say it's a city, is I think it's more than 10,000, 100,000, I think.
City?
100,000. Yeah.
Maybe yes.
Then
City
it's-
area, and I think you can...
and then the city, then Myeon, Dong. Dong is kind of village.
Ah,
Like
and
last.
so we took this data. First, we used their original giving region and constructed what, if we have this longitude and latitude, what region we should be getting. So this become the ground truth, the original data we hope to achieve. Based on this one, we started applying different algorithms. So K-mean clustering clustered Korea in this format based on the cities. And the error rate is about 65%. Compared to the original, it is not looking like it at all. When we apply density-based clustering, the error rate is also really large. And as we see, it focuses on the distribution of the city, not the clusters of the city. So this gives a very useful and insight meaning to the distribution of the cities. We can directly, by looking at here, think that, wow, Korea, most of the cities in Korea revolve around this region. And I will show you this in demo. But in our purpose, we want to cluster it into regions. So this is a failure. We tried the partition around Medioid. The error rate is also 67%.
Because we have big mountains here and all the way like this. Big mountains. So not many people live on the mountains.
So this is very insightful because for someone like me, I didn't know until this moment that there are mountains. But just by looking at this data, I can see there is some reason why this area doesn't have as much cities. So this is kind of a meaningful information we can get from a density-based clustering. We applied classification method, and we can understand directly that classification is going to perform better because it take advantage of the labels during the training. Here is naive Bayesian classifier, and it can achieve an error rate of 10%. SVM with a linear classifier, linear kernel, it can have an error of about 10. The best performance we get is the SVM with the radial kernel. We get about 3.8% error. So this is the state-of-the-art clustering and classification method. Then we tested our approach, our algorithm. So we constructed this single-layer network constructed from 10 perceptrons. We used rectilinear activation function, and we trained it for 3,000 cycle. The reason of using single layer is we want to check how the perceptron fundamentally behave. So we don't want to have a complicated network, even though larger layers will definitely perform better, but we are interested of seeing how it will perform in a very fundamental level. Performance, of course, is not as is expected to be very poor. We have an 82% error, but there is a catch at here. I put the table in here. We have originally 21 clusters, so there is something called random chance, meaning that if that clustering technique is so bad, it's basically just pure random, it will generate 1 over 21, which means 4%. So anything above 4% success rate is going to be better than random chance, which means it have the capability, it has the potential to do clustering, even if it is poor right now. And our approach actually is 17.8%. So it is better than random chance, which means it have the potential to perform better. We just need to make it wider and deeper. So this can be done in the next step. This was the first data set we tested. The second data set was called MNest, which is very popular and very widely used for testing of classification, but this is the first time we tried to use it for clustering. Clustering is going to be very difficult because the space is really nonlinear. In particular, each image consists of 28 by 28 binary pixel. So we are talking about 780 dimensional input space. And we are trying to cluster it again, not classify it, so it's become really difficult. The dataset consists of 60,000 training and 10,000 testing, again because it's for classification. We picked up 20,000 samples at here and 10,000 from here, and then applied our different algorithms. So for the network that we used in here, we used, instead of 10, we used 20 feature this time, and we use sigmoid activation function this time, and we only train it for 60 cycle, and then compare the result. Once more, the best approaches are classifiers because they take advantage of the labels, but our approach compared to normal clustering is comparable, and it is better. For some reason, density didn't work at here. I didn't check why carefully, but density just gave exactly 0% performance, density-based clustering. But the most important part is our approach is better than random chance. Here, the digits are from 0 to 9, which means 10 digits, so random chance is 10%. So we are well better than the random chance. So what is the conclusion based on this dataset? Before conclusion, I will just briefly mention that for this MNest dataset, Lee Kwon provided on his website his result as well. He tested based on this many other approaches, but he was testing it for classification, not for classification, not for clustering. So the numbers are here are not comparable directly to our number. I just put it for reference.
Make it slow. You have plenty of time.
Okay. So I put his numbers here for reference. I'm really sorry about this. So I put his numbers here for reference, but they are not necessarily comparable to us because he was using classification techniques, and we are interested in clustering techniques. So what is the conclusion? This is the most important part. We found out that best performances are coming from classification methods because this takes advantage of the labels, and in particular SVM with the radial and polynomial kernels achieve the best. In terms of clustering techniques, surprisingly, k-means turn out to be better than others. because k-mean is a linear clustering technique, so we thought it should not perform very well. But I think in our examples, the space was semi-linear, so it worked very well. In terms of
How the SVM was used
for clustering,
in the process?
yes. So let's say, for example, I will go about here. This is better. So in SVM, and I will show this in the live demo, we take 44,000. I think it's in the table here. Yeah, we have 44,000 set. We divide them into two sets. One set is 40,140, and we call it training, and we give it including the labels to SVM. And then after it finishes training, we give it a testing data set for cross-validation and check how much performance it can get at here. This is quite different than clustering, because in clustering I don't have the labels, so I cannot do this division. So I do self-validation, in which I try to cluster the whole space and see if this cluster's result is comparable to my origin or not, which is this one. So there are two different approaches for evaluation, one for clustering techniques, one for classification techniques. But the result is a success rate which is comparable, so we can compare both techniques at the same time. Okay. So these are the conclusions. The other conclusion is RBM is actually using L2 minimization, so it's actually following some gradient descent algorithm, and in that sense it is slightly comparable to density-based clustering, because every sample we get, it will affect our weight. So when we train so many times, it will be affected so much by the clusters that are nearby. They will actually pull the seeds too near to it. But we saw that the performance of our approach is significantly better than density-based algorithm. And the final comment is, even though the result right now seems to be poor, but it is better than random chance, which proves that it is having the capability of actually learning. We just need to train it in a deeper and wider network. Our conclusion is, perhaps before I go to conclusion, I should show the demo. So I will show two particular demos. This video I captured, in which I showed the implementation of R, but I think it maybe is a better idea to just show it in here directly.
You want to show here? It will not be recorded.
The video is recorded, so I can run the video in the background, but I think it's better to show it here. So this is the code. I shared all the codes and all the data sets on iCampus, so if you need that for reference, you can always find it. The first step is to import the data, and then sample the data and construct the origin, and then test one by one. So this is k-mean clustering.
We don't hear you.
Sorry.
Slow.
So the first.
What you are trying to do?
Yes. Perhaps I can also try to make it bigger, so it will be easy to see. Yeah, this is going to be better. So this is the code that I shared on iCampus. The first step is to load the data set. The second step, thank you. The second step is to prepare the data set for the clustering techniques. So this is kind of sampling. And then I will start to apply one by one of these techniques. So when I apply k-mean clustering, we can see the result directly coming out at here. And I write down the error rate. The functions to compute the error rate are here. Scoring, classifying, scoring, clustering are here, so you can also look at it if you're interested. Let's look at, for example, SVM linear. So it is computing right now. Okay, it's finished. So this is support vector machine linear. We can see the performance and the numbers. We can try different approaches. The best one, I think, in terms of performance is the support vector machine radial. So it appears at here with 3%, 3.8. The interesting part is the density clustering. So let me start with the density clustering. I suppose it's ready, so I'll just test. Perhaps I need to start with a smaller number. Maybe let's go for 1, 2. This is already large, so let me go for a smaller number. Maybe it's 0.4. I want to start with a small seed so I can show the growth of these seeds over
When
time.
you change it, what's the difference that you see?
This is something called sigma. So this is a density-based clustering. So whenever we have a seed, we will check within the sigma around this seed. If you have enough density, this can grow larger proportional to the amount of points nearby. So if I allow sigma to be increased, this means this growth will be aggressive, and we will see like this case, so in which most of the cities are clustered as one cluster.
One cluster.
But if I choose a smaller value, I'm trying to, it's kind of sensitive to the numbers, so let me try to maybe go for maybe 9. Oh, it's still giving an error. Maybe let's go for 1. Okay, so this is slightly smaller number, and if we increase it so far, it will be problem. But I want to show a very small number, so let me try to increase this a little bit, maybe 50, and go here from 0.5. I hope it doesn't generate the error. Yeah, so this is the beginning. The beginning is all of them are single cluster, and there is no seeds yet. Let's start to grow it.
Start from there.
Yes, I will start to grow it. So we start with the small seed at here. Let me grow it aggressively, maybe 1.5. I hope it doesn't grow very much. It starts to grow, as you see. And you can experiment with it. The code is available on iCampus, so you can play with it and see how this goes. But the main point is, even though as a clustering technique, the performance doesn't seem to, I grow too much anyway. It doesn't seem to be really good, but I'm thinking it's insightful in the sense that you can see the propagation of the density over space. So this can give an information as well. That is in terms of the clustering techniques. In terms of the classification techniques, in particular for the digits, Naeem have some demos. So let me put. You can try with different. Okay. Why it's not coming? Can you train just 3 and 3 iteration, maybe 3 units?
많고 빌리지가 많고 빌리지가 적은 거 그래서는 플렉스 간에 또그 정도가 나와 있었거든요. 그거를 생각하면 빌리지들이 그러니까 서울시 같으면 다 붙어 있다시피 하고 대식으로는 여기는 동료가 있고 그다음에 빌리지가 있으니까 센터들이 좀 떨어져 있을 거고 그러니까 그걸 덴시티를 표시하면 근데 대구가 잘 안 보이네. 신기하게 계속 대구가 좀 대구가 그 제3제 번째로 큰 도시인데 대구가
No, right? Just
아니면 데이터가 잘못 데이터가 잘못돼. 둘 중에 하나겠죠. 대구 경북이
so this is good. Let's go for
Yeah, and this is like you can change the number of iterations.
so the more the better.
The more the better. Don't try more iterations. Just try this one because it will take a lot of time.
You can expand if you want.
최소한 대구하고 거기 옆에 있잖아. 거기 영남대학이 있는데.
So this movie clip, I will explain it again. It will show the example of our code for the world cities of Korea in particular. The first line is going to load the data set, and then the second line is going to sample them and generate the original kind of ground truth. And then from here, one by one, we will test different algorithms. So the first one is k-mean clustering. We can see the result and its performance. Linear Yeah, SVM linear, and it takes time, but it will generate. This movie is about 4 minutes, so I'll try to jump in between. We can test all of them. The results are reported in the report we just explained. And the Bayesian classifier is going to take a little bit time and come out. For density-based classification, I explained the concept that if we keep increasing the number of sigma, it will grow, the seeds will grow more and more aggressively, and we can see it growing over time until most of Korea is consumed within as one cluster. Yes, sure. Sorry?
You will have the value of sigma, or you have
Yes, for density-based clustering, this is an input, so you need to specify the sigma. I didn't research this enough, so I don't know if there is a way to estimate sigma or not, but the algorithms we have are using sigma as an input, so you need to specify sigma at the beginning. Sigma will tell you, as you saw, sigma will tell you how much aggressive the seeds will grow. So once more, the density-based clustering may not be suitable for clustering Korea, but definitely give us a good insight of how the cities are distributed around Korea. It will allow larger circles when we check the neighbors for density, and then it will allow one seed to grow faster and aggressive than the others. Basically, it will not allow smaller clusters to have the chance to even exist. Yes. So yes. So basically, the red one will swallow this part before it even exists. That kind of idea. Okay. So that was the demo. So the final conclusions. In this project, we studied the behavior of a single perceptron. We explored the capability of using this as a clustering technique. We experimented on 2 different data sets and compared them to the state-of-the-art clustering and classification techniques. To best of our knowledge, this is the first time RBM is used directly to cluster world cities data set. And the results are maybe not impressive, but for an initial exploration are promising, especially that the RBM trained perceptron shows better performance than random chance, proving that this has the capability of learning. So the rest is just the summaries. What we need to do next, if we have the time, we should investigate in deeper networks and larger number of perceptrons, as the demo just shown by Naeem, my colleague. And this is the tools we used: R language for the experiments, and C++ and MATLAB for the testing of the neural network. And the references are here. These are the codes, so I already upload them in iCampus, so you can find them. It's much convenient than just copying from here.
여기 지금 코드도 올려줬고 데이터도 다 올려놨으니까 실제로 실행에 보면 똑같이 되는 것도 해볼 수 있겠지.
So the roles of this project, Naeem took care of the implementations of RBM training perceptrons using MATLAB, and he applied on the data sets and co-write the report. I took care of the implementation on R language for all the other techniques, set-of-the-art techniques, and comparison, and also writing the report. These are the final comments. So I will talk about my final comment, and I will allow Naeem to talk about his final comment. So I am definitely sorry, because this is a very interesting topic, and if I have enough time, I would pretty much interested to invest more time in here. So one thing is I didn't really have enough time to invest. I learned a lot. One thing is before we started this project, I didn't have any idea of how our language is being used. So I learned very quickly how to use it, thanks to actually you guys, because I learned a lot from you. I found the results of density-based clustering to be very insightful, despite the low success rate. The results of RBM training perceptrons are exciting, despite their underwhelming performance, as I said. I'm very grateful to Professor Lee and to the comments and discussions we had on iCampus. And most importantly, what I learned very quickly is clustering is not a trivial problem. Even for us as humans, when we look at something, we can have some troubles finding it. RBM training is not very efficient for clustering technique as of now. Perhaps it has a good potential. If we investigate more, we can get a better result. Deep network is definitely not a magical box. And one final comment is, if you remember at the very beginning of this, I said that people think that traditional classification techniques have the problem of requiring an expert to design the features, and they said deep neural network is better because you don't need an expert, you don't need to specify features. But I find it ironic because it seems to me like specifying how many layers and how many features require an experience about the task in hand, so it also reads expert. And I was really interested in the presentation of Payo because he actually explored different layers and different network, and the result is insightful. But I still he showed in his example, in his particular example, that 4 convolutional network is better than others, but he didn't answer why 4 in particular is better here and why not others numbers. So it's still a question, and I think it's not only in my mind, many other people in the research field are thinking about it. There are some insightful comments from Hinton in the references I put, but he definitely doesn't give an answer, the definite answer. He just gives a guideline, a very broad guideline. Naeem, if you want to...
Yeah, you may finish yours. But for the last comment that Naguib made, each data has special characters, like biological data and medical data and the insurance data are not same as the data from the industries.
Yes.
And so when you work in certain area, then you will deal the similar data. After you deal with it a couple of times, you will find kind of patterns. Then so you can easily find a better format that can deal with those data. But if you try to deal with all the different data with one tool, then like Mr. Pyo said, it may not work properly in there. So
that is very true.
Yeah. So yeah, you will see. Yeah, and for that reason, we better to work together. Who really know the data well? Then when you do learn their experience will be very helpful to find the best way to best method that you can use, and it will be very helpful to work with the specialist who has experience on the particular data to do modeling and to analyze. And Naeem, and you may finish.
Yeah, in my comment, I wrote some generalized comment, not particular to this project. Actually, what I learned from this class, especially professor gave us the task of presentation of the whole book. So that gave me some very insight. Some knowledge about the pattern classification, and it also helped me a lot to understand all the concept related to the pattern classification and recognition. Second, regarding to the project, we also tested our unsupervised one-layer perceptron, and we noticed that the result is not good as compared to the K-mean and also to the SVM. So one reason to this is all Naguib discussed. Maybe we use just one layer perceptron. So if we increase the number of layer, so we can get better result than the K-mean and other techniques like SVM and some other techniques. Also, like apart from this project, this class provided us the opportunity to communicate with each other, and it also provided us the opportunity, like we are friends and now we know each other, and professor gave us a very friendly environment to discuss these things with each other and learn a lot from this project. And he actually credit goes to the professor that he provided us this platform to discuss these things. So thank you all, and thank you, Professor.
Thank you. Yeah. Okay, good. Any questions or comment? Comment?
Okay, good. Thank you, everybody.